probably many of people don't know me. I just joined UC Berkeley about 2 years ago. Before that, I was in England 20 years. And before that, I was a UC Berkeley person. But the point is that in England, we don't have many earthquakes. So the point is that when I came here, I got to do something about earthquake because Pierre is here. And then actually, when we started, I'm going to show you some more work on the transportation network and the other water distribution network simulations that we're doing. And the reason why I started this was that we were quite interested in high-performance computing. And then I had a high-performance computing workshop with support from Pierre, and Tom came over to this workshop, and he showed me this particular, and this is Tom's slides, actually, and I did get a permission from him some time ago. So Tom's still okay, I guess. But the point is that he was talking about sort of a fragility curve from components to the bridge level, and then he said, let's go to the next level, single bridge fragility to corridor fragility, and then he started to say, well, we have multiple bridges, we may have earth embankment fills, we may have liquefactions, we may have slope failures, but for a transportation network, we're interested in which corridor is the most fragile and what is the fragility of the corridor level, which the Stanford colleagues mentioned about. And when I saw this, I think, maybe I can get involved in this particular activities that's going at Pierre. So how we started was that we were doing a lot of these simulations using high-performance computing for the transportation network. And then it's quite interesting, earthquake engineering. Earthquake is very important because when an earthquake happens, all the region in Bay Area get affected. Whereas if you have a small, one bridge, sort of a stop, collapse, or not, so one bridge being broken, then it's a little bit of that particular local area that affects. So for us, looking at the bigger picture and looking at city scale model was quite attractive in terms of high performance computing as well. So Jack Baker provided us with some sort of a different scenarios, and this is where we are starting from, is that you have this particular sort of peak ground velocity scenarios, and he has provided a software for us to try different type of scenarios. And in our particular project that we're having as a seed funding is really looking at from that scenarios, what are the bridge closures that Jack was supposed to give us, so we'll get that. And then we'll do these traffic simulations that we're going to do. So I'm not sure Stanford guys knows about that, but that's what Jack promised us to do. And then also we have this water pipe breakage, which we've been working with East Bay Mud on the water network, so I thought that would be an interesting one as well. And then the final goal is to combine bridge closures and water pipe breakage, because when an earthquake happens, not individual only bridge breaks, but water pipeline breaks. So how's that connected together, and then do the traffic disruption at the city scale. So in terms of our project overview is to look at distributed agent-based model. Some of you probably know the agents are how people move around the city in this particular cars at the city traffic simulation scale on using a graph network. So we use this kind of a graph theory that is coming, and you can see that graph theory is coming very much nowadays because of the Facebook and Google and Twitter, because if you do Facebook, you're connected to some person, so that gives you links, you're the nodes, and then they work on huge network of people connection, and there's a lot of activities going on to optimize that particular network simulations. So we are utilizing that particular one and looking at sort of a traffic congestion by bridge closure scenarios provided by Professor Baker's team, and then pipeline breakage scenarios for East Bay Mud. And again, state-of-the-art graph algorithms like shortest pass algorithm or PageRank. If you know PageRank, Google tells you which page is the most important one. They do this sort of a network of graph theory to find out which page is most important. And the idea is utilizing these sort of techniques, can we do some sort of a multi infrastructure simulations. So let's start with the road traffic network. I'm sorry, the light is not very good. I'm not sure we can darken the light a little bit better. But this is, actually, I came from London, UK, so this is a London sort of a network, sort of street level. And then you can go up to the sort of a London scales level. And again, it's a sort of a nodes and links, it's sort of a grand network. So when I was in UK, we worked on working with Google, looking at which street is used the most. So they were providing, it's exactly what you get with your Google Street, a Google Street Map, is that how density is used and what traffic is used. So if you do that, if you look very carefully, actually the vertical axis is the how much is being used, and then horizontal axis is week. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then I'll show you the traffic of the northbound and southbound. And in this particular road, the northbound is always busier than the southbound during the weekdays, but in weekends it's the other way around. So why that is? But then the point is that you can get these data set as a real-time data set of that particular road. And by doing that, what you can do is that you can do what we call a volume delay functions, where you have a speed in your vertical axis, and the horizontal is saturation, means that how crowded the road is. So if you're not crowded at a road, it's speed 0, and that gives you a free ride speed. Of course, people tend to drive not following the speed limit, and therefore, in this case, eastbound is people go faster than the westbound because of the certain signs and bus stops that they had at that particular location to give you a different one. But these data points are really coming from the a Google data sets that you see. But the point is that by doing that, you have a characteristic of a model for that particular road with particular characteristics of how speed is, how the road is used depending on the congestion. So with that model, and then if you have to also start, when you do agent-based model, we'll start where the people start and then where they stop, and that's called origin and destination. And for example, California House Travel Survey has some data set for the East Bay. So starting where you start from certain place in the East Bay, and then where do you reach? And you can populate that to create some agents. In San Francisco, people use Uber and that sort of thing. So Uber do provide data sets of origin and destination, so we can utilize that data set as well. And by doing that, what you can do is that you can start to seed these agents and then start traveling in the city to create a congestion. And of course, Google data set, that traffic data, will be the calibration data set that you can use. So what you can do is that you can simulate, this is a San Francisco, I'm not sure you can see, I'm sorry about this, but then the light, if you see a light moving, that's how people are moving around the city. And this is for the San Francisco city using the Uber origin destination. And then you can do that for the entire Bay Area network in terms of San Francisco, Berkeley, and the area that you see people moving around. So these are agent-based model. And then you use these a Google traffic data and other things to calibrate your model. And by doing that, you can say, okay, if you start with smaller number of agents, but then eventually you have to have an entire network with lots of agents to create this congestion. So if you have 400 agents, meaning that there are only 400 cars running in this particular street, then it's always free ride. But when you start increasing, this is 40,000 agents, you'll see something, start to see Bay Bridge start to get congested. And then if you go to 50,000 agents or even go to 1 million agents, you start to see more realistic congestion happening. So what this allows you to do is that you have this simulator of the traffic simulation, and then let's say if you close the Bay Bridge, what's going to happen to traffic? Because what we do is that we use shortest path algorithm for a given congestion of that particular time. So for example, if you at particular time of the day, earthquake will happen and then the bridge get closed, and then the people start to divert, and then you try to do the simulation of that, and that's what agent-based model is about. And now you start to realize that we've got to do a lot of these shortest paths and agent, a large number of agents moving around, and that's where the high performance computing comes. And so my colleagues are working on this, and of course I'm not the expert, my students are the expert, and my postdocs are the expert, and looking at using a high performance computing, how fast we can go nowadays. So this just shows how many processors we have in terms of how many seconds to simulate a number of person. 1K is 1,000 people, 40,000 is the grid, and as you can see, more processor you have, but you do have some a saturation, even you have more processor because of how you transfer the data, just stops making faster. But typically at the moment what we have is we have 40,000 agents, sort of a simulation within 120 seconds, which is 2 minutes. So the current CPU implementation using 32 processor, if we say if we simulate 1 million people, which is 10% of Bay Area population, who's probably traveling around in the Bay Area using cars, then we can run one simulation in 47 minutes. That means that every hour we can update things. But then we're interested in going faster. Of course, that's what we're always interested in as an academic. You can go to GPU option. GPU option, you can go 100 million agents, and it runs in 10 seconds because of the GPU. But GPU problem is that each GPU can't handle very large number of agents. So we have a problem, nodes. So then we have a problem. So now we're working on trying to combine everything, and eventually we can go to, hopefully to go 10 million agents, which is the Bay Area population in 2 minutes interval. So that's our current goal that we're going for. But having this particular network is where our interests are at the moment. And as we discussed about graph theory, if you have a network, you can utilize some of the state-of-the-advanced, state-of-the-art tools to say which network, which part is sort of a critical. I see some of Stanford colleagues looking at which network is very important. There are a variety of algorithms available, and that's what it does. So if you do sort of a Google page type of page ranking on this particular entire network of the traffic, you can see the reddish color means that these are important nodes, for example. You can do the same thing for the water network. So this is the East Bay Mud network. So East Bay Mud provided us the entire network of the East Bay Mud, meaning that if you have an earthquake, Jack will hopefully give us, and then we go to the how pipeline will break. And then again, you can do, so this is the entire East Bay Mud network, and it has about 100,000 nodes. And again, you can do a page rank, but then as we understand that traffic flow is one thing, but also water network is another, but we do have a physical model of how water moves between the pressure and the flow. So now what we want to do is to simulate the water distribution, meaning that you have a network where you can do basically like a finite element analysis of the pressure versus the flow, flux. And you can do that. We're currently working on this particular one with the entire East Bay network. So you start with a very simple one using Python. Our current one goes like this. So at the moment, we can solve one iteration in a sort of 2 minutes level. But now we're currently developing an HPC C++ code to simulate this entire network in seconds. And you may say, okay, somebody must have done this, but it's quite interesting to see that there are codes available in the market like EPANet or WNTR, which is sort of a commercially, a publicly available network, but they don't do really city scale. So what we're trying to do is to go for 1 million nodes, as you can see in the sort of a first row over here. And what we're trying to do is to simulate the hydraulic analysis based on that particular scale. And how fast can we go? And that will be interest to many of you. And again, you are developing a C++ code with a GPU support. And ultimately, if it's like a typical East Bay Mud network, we have about 100,000 nodes. And if you're doing finite element, it's really doing a finite element analysis using that sort of metrics at simulations. And we probably can, currently we can go about 15 to 20 seconds. And if you go for a much bigger network, it's a 30 to 40 seconds interval. So in summary, what we're trying to do is to show, sort of start with what Jack can provide us with a brick closure, and then from East Bay Mud, they're providing the water pipeline breakage and trying to demonstrate how this transportation network simulation can be used for a peer community. So year one deliverables, we only have funding for 1 year, so that's all we can do. So earthquake effects on city scale traffic, bridge closure scenarios, pipeline break scenarios, or combined, really to demonstrate that changes in travel time. So we look at the sort of commuter level, looking at 1 million agent to start, which is a 10% of the population of the Bay Area network. If our peer colleagues are happy, we can go further, and future deliverables may be more on the. So in a sense that 10% is sort of going through the sort of commuting. But then when earthquake happens, probably everybody get sort of worried, and then not only 10%, but more people may start moving. So in that case, we may have to think about entire population of the Bay Area, which is about 10 million people. So these are something, it's reachable using the current HPC techniques. So that's what we're trying to do. And then against a water neck or fragility is that we can start to simulate the entire East Bay Mud network, and that's what we are trying to deliver as well. And of course, Khalid will say, oh, what can you give it to me? So I'm sort of thinking maybe there's some web-based applications of the Bay Area networks in terms of water and traffic, etc. So that's all I have. Thank you very much. So any questions to me? Yes. I'm not supposed to do that.
I think this is awesome. I really like this. I have a question for you. Since you're collecting data every day, we are, right? I mean, there's enough data out there. And Khalid was talking about artificial intelligence. Can you use that data to improve? Because you said you use the shortest path algorithm, which I'm a big fan of because I use Waze, but it's not really the shortest path for me. It's actually the fastest path.
Yes.
So it's different. It's completely.
It is the fastest way, yeah, because we use weighted function for each road, and that becomes the fastest one. So it's not shortest path.
Right. Okay.
Yes.
So it is the fastest.
I think it depends on the agent that you can see. So agent may say I want to go to least length, or you can go to so you can also change that.
Right. It's not
yes.
Everybody does the same thing.
No.
But can you use real-time data? So, for example, if the day that they close the Bay Bridge, or if there's a lot of traffic on the Bay Bridge, can you look at, based on just the everyday data, what other routes are people taking? Are people, if there's a big congestion, or because we know there was an accident 3 days ago
yes.
on that bridge. Can you look at that data and therefore improve your models?
Yes. That's exactly what we need to do, and that's why we want to update. And then any small disruption we can learn, and the agent will learn to do something. Of course, agent may not do the same thing when the earthquake happens, but that's another issue.
But it may be better. It's an improvement.
Yes.
It's a less bad model.
That's right. We hope that is. Yeah. You're absolutely right.
Because you're collecting so much data every day.
Yeah.
That'd be neat to see that being used.
Yeah. Thank you. Yes. Absolutely right. Yeah.
I was wondering, just out of curiosity, you are collecting a lot of data under, let's call it, service conditions. So there is a certain psychology of these agents that is moving. I could imagine that in a case of an extreme emergency, there may be visual phenomena, there may be sounds, there may be fires, there may be things that trigger illogical behavior
yes.
or unexpected behavior.
Yes.
So would you be able to, let's say, use this in actual cases of an earthquake, let's say in Tokyo or in Osaka or someplace, and make sure that your model is also good for
yes.
extreme conditions?
I think the spirit is yes. Yeah, how we get that data, because the point is that is really giving information to the agent, how the agent behaves from the origin.
Right.
What is he or she is going to do.
Right.
And that's a little bit more of a human behavior side of modeling, and our colleague like John Walker and all these people who work on that will be able to contribute to that scenario. I think at this stage is really to show that, yes, we can do the simulations, how are we going to go forward. But you're absolutely right, and that's the trickiest part, I think.
Massive psychology.
Yes, yeah. But I'm not sure Pierre wants to go to that direction.
There is funding, you can.
Okay, so I'm going to stop, and then let's go to the next presentation.